Welcome back, guys. Let's talk about a slightly more complex case, or the next most complex case, relative to the simple uh, unimolecular kinetics we've been discussing, right? As you recall, right, a simple unimolecular process looks something like this, just A goes to B, right? And we got to look at the fact that the temporal dependence of the disappearance of A is simply equal to the concentration of A0 we started with, and it's an exponential function then of e to the minus kt, where k is that first order rate constant. Okay, well, these first order reactions are common. They occur quite a bit. At least as common, if not potentially significantly more common, are so-called second order or bimolecular reactions, right? And so that would look something more like this. We had A plus B now goes to AB, right? Or it could be that they react, right, with each other, maybe, and so instead of A plus B, maybe they make something C, whatever, right? A plus B would look sort of like a binding reaction. That would be equivalent to sort of the binding kinetics, right? A plus C would be a chemical reaction, right? In either case, the basic temporal kinetics are going to follow a similar sort of process, right? Which is, like I said, a so-called bimolecular where two things have to come together, have to interact, bind to each other, right? Now, this process, bimolecular reactions, are also going to have an associated rate constant. Again, remember, we're talking about rates here, so we're using lowercase k, we're not thinking about equilibria. And we want to, like we did with unimolecular reactions, we want to come up with an expression that lets us describe the temporal change, how the concentration of A changes with time. Okay. Now, turns out there are two ways to think about a process like this. In one case, you can think about a bimolecular reaction under conditions where the two things are the same, right? Say, so a simple dimerization reaction, right? Where the reactants are the same. Right, so like I said, that would be equivalent to like a dimerization process. Alternately, second case is where the reactants are not the same. Explicitly not the same. All right, and that one's a little more complicated. So let's deal with the easy one first, right? All right. So what would that look like if we were going to write out the sort of model, the kinetic model for dimerization? That, of course, would look something more like this, right? We would have, say, A plus A goes to, well, we'll just say maybe they react, maybe they dimerize. Again, you could write this out as A squared if it was a dimerization, right? So well, we can just do that, right? We can call it A sub 2, right? So it made a dimer, right? With an associated rate constant. Okay, so we're thinking about this explicitly, as I said, as a dimerization reaction, right? All right, and the rate equation for a process like this would, of course, be, as you recall, we're thinking about the velocity, remember, which in case we're thinking about A disappearing, right? Minus d derivative of change of A, concentration of A with respect to time. And in this case, we're fairly easy to write that down. That would, of course, then, in analogy with how we did this before, would have to have that rate constant times concentration of A times concentration of A, right? Which means that our rate equation here is simply written as this, right? Okay, fairly straightforward, right? Now, a couple of things that's the rate equation we need to figure out how to solve. Before we get there, let's consider a couple of things. First, think about the units for this so-called bimolecular reaction. Excuse me. Or the bimolecular rate constant. What are they? You remember for a unimolecular process, it was just inverse time per second, per minute, per hour, whatever you wanted. But remember, the units over here, this is still going to be, molar per second, for example, unit, concentration per unit time. Well, here we've got concentration squared. We got to get the time in there. That means the units for this bimolecular rate constant have to be per molar per second, right? Or per molar per unit time, right? Okay, I could say that could be per molar per minute, whatever, right? But the bimolecular reactions, the rate constant has different units than a unimolecular reaction, right? It's got to be per molar per unit time. Okay, all right, that's cool. One other thing to note, like I said, I've been calling these bimolecular reactions, right? Because we have two things, right, that interact to do something else, maybe form a dimer in the case we're considering. These also get another name sometimes because the mathematical form of this differential equation. We're again dealing with an ordinary differential equation, but you'll notice that the variable now, instead of being raised to a power of 1, is raised to a power of 2, right? So what that means is that the simple bimolecular or relatively straightforward bimolecular reactions are also sometimes known as second order reactions, because this is a second order ordinary differential equation because of that exponent in the variable. Okay, all right, so now we need to solve it, right? All right, so in this case, the easiest thing to do is to more or less use the mathematician's way, unless you just basically have the integral tables for this, like, embedded in your brain. So simplest thing to do, I'm just going to write it out again, get away from all those scribbles, where again, minus rate equations minus concentration of A with respect to time, it's going to equal K concentration of A squared, right? And so now we need to solve that. So like I said, the rigorous way is probably the easiest way to do this, where you separate your variables, the concentration of A divided by A squared, integrated from A0 to A, right? And that's then going to equal, of course, like we had before, T0 to T. And we can, again, pull the minus and the rate constant outside the integral, T, right? Now, you go through and run that integral. Not such a big deal. It's a fairly easy one. What you find is that your rate equation now looks something like this. 1 over concentration of A as a function of time is equal to 1 over concentration of A we start with plus KT, right? That is the solution to the rate equation, or this is basically our dimerization rate law for the solution of the kinetics for a dimerization reaction. Fairly straightforward, right? Not such a big deal. Not too hard, right, to think about. But there's something really important to look at here. Remember that for that simple first order reaction we talked about before, right, that unimolecular reaction, I'll just write that down here again so you get the form in your head, right? Remember that the T1/2 of this process was completely independent of protein concentration. There was no term in here for the protein concentration. That is not true in the case of a dimerization reaction. If you solve that equation for the half-time, what you find is that for a dimerization, the second order dimerization reaction, the T1/2 is equal to 1 over K, that bimolecular rate constant, times A0. So in the case of a dimerization reaction, the T1/2 very explicitly does depend on the concentration of A you start with, whereas in the case of a unimolecular reaction, there is no dependence on the starting concentration of the reactants. Okay, so that's the easy case, right? What about the more complicated case? All right, so this is sort of like our case 2. Right? What happens when we have something that looks like this? It's not explicitly, let's say, a dimerization, right? Maybe it's a binding reaction, but A and B are different. They're not the same thing. Okay. For this, things get a little more complicated, right? And as is often the case mathematically with solving differential equations, which is what kinetics in many ways ultimately comes down to, the form of the solution can depend very explicitly on the initial conditions of that are chosen, right? And that's also true in the case of this more general sort of binding, bimolecular, so-called bimolecular binding, or more general bimolecular reaction. All right. So how do we approach that? Well, again, we're gonna have like 3 subcases of this guy, right? Where our initial conditions sort of set the space of what the solution is going to look like. The first case is easy, it's really easy, right? If the concentration of A exactly equals the concentration of B at the beginning of the reaction, then the solution to this bimolecular kinetic, or the rate law describing this process, is going to look just like the dimerization. Right? The form of the solution basically looks exactly like the one we just solved, right? In the case where concentration of A equals the concentration of B. All right, so that one's easy. So we can dispense with that one. All right. What happens? Oops, wrong color. What happens then if the concentration of A does not equal the concentration of B when we start the reaction, but neither is in large excess? And what I mean by that is A is less than B, or concentration of A is greater than B, is somewhere, in both cases, somewhere less than, say, 10-fold difference, right? This is the more general case, right? And the solution here, this is the sort of general, as I said, general solution to this simplest possible bimolecular reaction kinetics, right? But it's also a little involved. Not too bad. I mean, it's not terrible, but it would take a page or 2 of derivation to get to the end. Form of the expression is not so bad, but there's sort of a practical aspect to this, even though it does occur and it's relevant in many cases experimentally. One would not study a reaction like this, right, under this set of conditions, if at all possible, right? And the reason is in part what I'm explicitly describing now, which is that the general case is form of the kinetic equation, or the rate law, is significantly more complex. And so if at all possible, one would not work under these conditions, right? Sometimes you don't have any choice and you have to utilize that rate law in order to characterize the kinetics. But if possible, you would probably try to choose the third subcase here. And in this case, you go out of your way to study a system like this under conditions where the concentration of A is much greater than the concentration of B, or the concentration of A is much less than the concentration of B, right? Now, this particular subcase, this particular set of conditions gets a special name, right? This is known when you're studying a process like this as so-called pseudo first order conditions, right? And you'll see why it's called that in just a second, because we're going to go through the solution of this. And this would be the experimentalist conditions of choice for studying a biomolecular reaction and trying to characterize the kinetics if the system lends itself to being studied this way, because it makes life a whole lot simpler, as you're about to see. All right, so what is the solution to the pseudo first order conditions look like? Well, let's go back first and write out what the basic rate expression might look like. Again, I'll just remind you guys, the basic scheme looks like this, right? And we get this rate constant here. All right, so let's say we want to know how fast concentration of A changes, right, with time. Okay, that's just going to be equal minus dA dt. That's just going to be equal to K concentration of A, concentration of B, right? Not so bad. Except we got to solve that differential equation if we're going to do the general case. But remember, we're under pseudo first order conditions, where we're going to assume that concentration of A is much less than concentration of B. And let me be a little more explicit about that. Let's say A0, our starting conditions here, right? Okay, well, if the concentration of B is a lot greater than the concentration of A when we start, is the concentration of B going to change much? Right? If there's 10 times more B, and the molecularity of this reaction is written out as 1-to-1, at most, right? It's going to be like a 10% change. And if you're higher than that, it's going to be even less. So under these conditions, when this is true, the concentration of B is approximately constant. Right? That's really useful. The reason that's really useful is because we can basically do something like this. We can say, well, then the rate of change of A with respect to time is just going to be equal to now the biomolecular rate constant times the concentration of B at time 0, right? Which again, like I said, is approximately going to be constant times concentration of A. All right, well, we know, okay, that's a constant, right? And now we're saying that's a constant, right? Because we're saying we're in large excess, so it's basically not going to change very much. That's cool, because that means I can define a new constant. I can say, well, I can just put these two guys together. I'm going to call that K prime, right? So we're going to say K prime is equal to the true biomolecular rate constant, K, times the concentration of B that I'm using. All right, that's useful, because I can rewrite this expression now. And it's like, now, minus D concentration of A with respect to time is just equal to K prime concentration of A. Now, does that look familiar? That's exactly the same rate law that we, or rate equation, rate law expression that we derived for the simple unimolecular process. Remember? That was minus D concentration of A dt is just equal to K concentration of A. The mathematical form of that expression is exactly the same, which means the solution of this rate expression, rate equation, to find the rate law is exactly the same as we used before, right? So if you go through and you solve it, what that means is the change in concentration of A as a function of time is simply equal to concentration of A0, right, times e to the minus K prime T. But we're again remembering that K prime here is not like we had before. K prime is equal to the true bimolecular rate constant times the starting concentration of B. Now, maybe some of you have seen this before, maybe you're already developing the intuition. Now, the question is, how do we get K, right? Remember, it's the true bimolecular rate constant that we want. Well, it turns out that's actually pretty easy, kind of like we did with the method of initial rates. We had a series of experiments, and then we plotted the results of that to get a value. And like we're going to do again, we talked about Michaelis-Menten kinetics. The solution here is relatively straightforward. Using that expression, right, we would then do a series of kinetic experiments, function of time, right? And we're looking, again, we're measuring concentration of A. Up here is concentration of A at time 0, where we now do a series of experiments, right? And for each of these experiments, what we're varying now is the concentration of B, right? So down here, this expression, this one, we'd have concentration of B at time 0, say 1. Here's concentration of B at time 0, 2. Concentration of B at time 0, 3, so on and so forth. So what you can see is that as we increase the concentration of B we have at time 0, which again is approximately staying constant because it's in such a large excess, the reaction kinetics are going faster, right? Because we've got more B available, right? So as this goes up, concentration of B0 goes up, the reaction gets faster. Well, that's cool, because now what we can do, if we fit each of these, right, and we would have, we'd have some data in here, right? If we were going to really do this. That's cool, because now if one went in and fit those and extracted from them K observed values, right? So observed rate constants for each of those conditions. You could then take each of those K observed values and plot them, right? So we're looking at K observed on the y-axis, and now as a function of concentration of B0 on the x-axis. And what would it look like? If you go back up and you look at our definition of K prime, which is now effectively, what I'm now calling my K observed, right? Right? It's just a line, right? K observed is going to depend linearly on the concentration of B0, and the slope of that plot is just going to be K, right? So that's it. We're kind of cool, because that means we do this, right? We plot those babies out. We have a series of experiments at different concentrations of B0, and the slope of this line then gives us the true bimolecular rate constant, because that K observed is simply equal to K times the concentration of B0, right? Okay, so these are the so-called pseudo first order conditions that you would use in a situation where you really wanted to study a bimolecular reaction and you didn't want to have to grapple with the general solution, but you wanted to quantitatively extract that bimolecular rate constant. Using pseudo first order conditions is a way to do that in a relatively straightforward way by running a series of experiments and then plotting the K observed values, right? Okay, talk to you next time.